Hello and welcome back to another LeetCode practice video where I just practice solving problems, and I'm using LeetCode.io to keep track of my completed LeetCode problems. It's nice because you can just check items off here and it remembers it. And you have a list of curated problems that's based on the blind 75 list and was expanded to the LeetCode 150 list. So you have more to practice, which is of course always fun. And yeah, I've been doing all of these backtracking problems so far. I'm slowly getting the hang of it, but I still struggle with the runtime complexity. And because of this recursion and the branching factor and all of those things. So let's see what the next problem holds for us. Let's see. So I've tried this before last year. I'm not sure if I can still do it. Hopefully I can. Let's just have a look at it. So 131 palindrome partitioning. You are given a string S. Partition S such that every substring of the partition is a palindrome. Return all possible palindrome partitionings of S. And okay, S has at least one character and S contains only lowercase English letters. Nice. And so there are some examples here. So how can we split this into palindromes? We could split this into AA, that's a palindrome, and B. Yes, so that's a valid partitioning, but also every single character is a valid palindrome. So splitting S up into its individual characters is always also a valid partitioning. Nice. And here's another example where S is just one character. And yeah, a single character is a valid palindrome, so that works. Cool. So we're going to do something with backtracking, which means we're going to do recursion again. I struggle a little bit with giving runtime, time and space analysis and of whatever space before actually implementing it, at least for now with these backtracking problems. You know, we have seen like n factorial runtime in space. We've seen 2 to the power of n runtime in space, etc., etc. So let's see what we get with this one. I don't know yet what it will be. Something like my gut tells me we'll have something with probably 2 to the n and space time, and something maybe linear in the space. Because we're taking the string, we're just splitting it up in different ways. Right? But yeah, I don't know yet. Let's see. Well, the cool thing about backtracking problem is we always have the same structure. So even if I don't know anything, I know that I need the structure helper, and we'll call the helper. Helper. We call the helper function. We return a result, but and we have to have a result variable. And since we're building up things here, we probably need a list to which we add all the valid partitionings. And now I'm thinking that if we iterate through our string, maybe we should go into the recursion after every character. And the condition is that the previous characters are a palindrome. Right? So in our recursion, in the recursive helper, we could have a loop over all of the remaining characters and always check whether it's a palindrome. And if it is, that means we can make a split at that position. So if A is a valid palindrome, okay, then, oh, boom, nice. We're going to book A as part of our valid partitioning, potentially valid partitioning, and we continue to try to find palindrome partitioning from the remainder of the array of the string. Right? So we're just going to be greedy, but then we will backtrack, and the next time we will try to check, is AA a palindrome? Oh yeah, it is. So we add it to our potentially valid palindrome partitioning, and we continue trying to find palindromes from string B onwards. So that's going to be the idea. Very nice. And so we need an index that tells us from where to start. We also need to know well, what the next partitioning is, right? Partitioning. So we're going to build up a partitioning or a partition of all possible palindrome partitioning. So yeah, it's called partitioning. So we pass the start index, we pass the partitioning, and we need the termination case, and that is if length, well, if start is larger or equal than length of our string. What does it mean? That means we found a valid partitioning, right? Hopefully that's what that means. Well, that's what we're going to make it mean. In that case, we add this partitioning to our result. Result.append append the partitioning. I'm going to make a copy of it. You can do that like this or just do copy. But I like this. I like this. Otherwise, well, we still have to check, right? If we have a valid partitioning or not. And so with backtracking, right, we build up the solution with every step of the recursion. Then when we reach the end of the recursion, that tells us that what we build up is a valid result. That's why we copy it here. And when we do backtrack, we might add or remove elements from our partitioning to rebuild them, to try all the different paths in our search, our depth first search. Cool. So yeah, so how do we do that? Well, for I in range, start to length of the string. So we're going to try to find a palindrome from the start to the position I. That is the goal, right? That's what we need to try to do. And so, well, we need something that tells us whether it is a palindrome or not, right? So if or need a helper method is palindrome from start to I, then that means we can add this string to our partitioning. Append. Now we take the string S from start to position I +1, right? Yeah, +1, because the end is not inclusive. Right. And then we do a recursive call, and we'll continue trying to find valid partitioning for the remainder of the string S. And after that, we're going to pop this palindrome that we just found. We're going to pop it out and continue to find another one that is even longer. Right, so that's what we will do here. And we're going to call helper. And now our new start is going to be I, right? But we have to do I +1. Since we've already, well, we used the string all the way up to I. So in the last case, when actually this points at the end of the string S, that'll trigger this, where the start is then larger and we're done. So we will do this. We will pass in the partitioning. And that is pretty much it. I mean, we're going to compute a hell lot of palindromes, but I think that's what we need. So the second helper function is if def is palindrome, we get a left and a right index, left, right, and then we just check whether something, well, the string is a palindrome between those indices. While left smaller than right, by default we return true. If s left not the same as s right, return false. Otherwise we will say that left gets increased and right gets decreased. So this is an O of n time O of 1 space is palindrome checking algorithm, and you should be familiar with that from from, I guess, previous problems, if you've watched them. So we're not using any extra space. We're accessing the characters directly from the string S. So if this is, okay, let's check. So if this is a palindrome from, well, we start from, do we have to increase this to +1? No, not really, right? If left and right is the same, right? So if we're checking if a single character is a palindrome, it will return true because it never enters the while loop. So that's fine. That's absolutely fine, I think. Yeah. I think that should work like that. I think that should work. If it's a palindrome, we're adding it. Then we try to do this with, okay, let's just walk through an example instead of poking around here. Maybe we start with example number 2. That should be easy. The partitioning doesn't exist in the beginning, so we have to fix that here in the helper. And we can also do it like this, return result, and then we just return the helper. Cool. Yes, so let's see. So we start with A in our string S. Start is 0, partitioning is empty. The start is not larger or equal than the length. So we just iterate over all of the indices from 0 to 1, 1 exclusive. Now we check if actually from 0 to 0 is a valid palindrome. We check that case, that is true. So we're going to append this partitioning of the character at position 0 to our partitioning array. And then we're going to call the recursive function. Now the start is 1. And we run into the case where the start is larger or equal than the length of S, which is also 1. So now we're going to copy the partitioning of A as a list, and we're going to put that into a result. So we should get exactly this. That's what should happen. And if we go through example 1, let's do that real quick. So we pass that in. Well, we find that A is a valid palindrome. Nice. We don't run into this case. So now we're checking if the other A is a valid palindrome. So that should all work out. I think it's fine. I'm just going to run it. I don't want to drag this out unnecessarily. Oh, woo, that works. No syntax errors, nothing. Wait, I'm actually surprised. And let's submit it to see if that works. Okay, and that works. Great. So now space and time complexity. All right, so here's now a reason or a way to reason about this stuff. Because at every position I, we can make the decision, well, every time we find a palindrome, we can decide to make a cut or not make a cut. And because we have a binary decision to make, that means we have 2 to the power of n. Because inside 2 to the power n. So here, if we have a palindrome start, if we have a palindrome, we can decide to make a cut here, which is the recursive call, or we could decide not to make one, which is the continuation of the for loop. Now, since we're iterating over n elements at every point, I believe it's n times n 2 to the power of n time complexity. Now, in terms of how many elements are we going to get? Well, in the worst case, everything is A, right? We could have lots of A characters. And how many ways are there to partition them? Is it linear? Or is it quadratic? Or is it also 2 to the n? Maybe we can get an idea by just going through some examples. So let's say I have only one A in my string. The only partitioning I have is A. Let's say I have two A's. And then, right, the worst case is when the string consists of all the same letters, then every substring is a valid palindrome, right? That's kind of the worst case. So the first partition would be AA, and another one would be, well, AA. Now, if we have three, what can we do then? Well, we can pick the three individual, or we could pick the first A and then the other twos, or we could pick the first two and then this. What if we have four A's? So this seems to be like a linear growth. We have four A's. Then we have maybe, we can pick two A's and then two A's individual. We can also pick 1A, two A's and 1A. We can also pick two individual A's and double A. Now we can also pick three A's. No, wait, two A's and two A's. We can also pick three A's and 1A. And we can pick 1A and AAA. So here we have 1, 2, 3, and this is 1, 2, 3, 4, 5, 6, 7. 7. So this is there logic in here? So the difference here is 1, it's 2, it's 4 now. Well, that looks like an exponential growth, doesn't it? What if we do it one step further? Wait, is there a systematic way to construct these examples? Let's just go one more step. I know this is cumbersome, but let's see one. We can have 4 A's. We can have a double A followed by 3 A's. We can have 1A followed by double A followed by 2 A's. We can have two individual A's, a double A and another individual A. We can have 4 individual A's, no, sorry, 3 individual A's followed by a double A. So how many is this? 1, 2, 3, 4, 5 so far. And now we can deal with the other double A. Sorry, 1A, a double A, a double A. We can have a double A, an A, another double A. We can have double A, double A, A. That's another 3. Plus 5, plus 3. And we can have, well, the 3 A's, right? 3 A's and 2 individual A's. We can have 1 individual 3's like so. We can have 2 individual and a triple A. And we can have a triple A and a double A and a double A and a triple A. That's another plus 5. Then we can have 4 A's and an A. And we can have an A and 4 A's. Another plus 2, so that's 10, 15. So that's now 15 for 5. So is it like it doubles every time? 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16. It seems to be 2 to the power of n, or at least asymptotically. So that would be my guess. 2 to the power of n space. Because all of these are valid partitionings, right? Yeah, and that order of magnitude. So yeah, so that concludes that problem. Give it a shot yourself. And maybe you know something that I don't about the runtime and space complexity analysis.